start with a black screen. A single, faint mote of dust appears. There is a silence in the cosmos that predates sound itself. It is a quietude of impossible scale, a vacuum stretching between worlds, and in this profound emptiness, there is only light and time. We think of our existence as a solid, continuous thing, a life, a civilization, a world, firmly anchored in the here and now. But from this perspective, from out here in the great dark, it is something else entirely. It is a flicker, a brief, incandescent spark. That spark is our sun, a single, unremarkable star among billions. And it is our starting point for a voyage that defies all human scales of distance and time. We are embarking on a journey not of physical propulsion, but of perception. Our vessel is an observatory of the mind, a craft that can navigate the ancient streams of light. It allows us to arrive at a distant shore at the precise moment its story, carried on photons, finally reaches us. We are undertaking an impossible pilgrimage, a real-time passage through every kind of galaxy in the universe. To begin, we must first understand our own home. We pull back from our solitary sun, past the orbits of our planetary siblings. The familiar constellations warp and distort, their stellar members revealing their true, vast distances from one another. Our local neighbourhood dissolves into a swarm of luminous points, and as we retreat further, a structure begins to emerge from the chaos, a breathtaking swirling pattern of light, dust and gas. This is our home, the Milky Way. For millennia, our ancestors looked up and saw it as a faint ethereal cloud, a spilt trail of milk from a goddess, a celestial river, the pathway of souls. They were not entirely wrong. It is a river, a torrent of 400 billion suns, a colossal, barred, spiral stellar metropolis, 100,000 light-years from edge to edge. Its form is a masterpiece of gravitational architecture. Great sweeping arms of dust and newborn stars, the Sagittarius, the Scutum Centaurus, the Perseus, spiral outwards. Our own solar system resides in a minor spur, a quiet celestial suburb known as the Orion Arm. From our vantage point, we are nestled deep within its plane. This is why it appears as a band across our night sky. Imagine living inside a single page of a gargantuan book. You could see the words on your page, but the shape of the book itself would be a mystery. For centuries, this was our cosmic predicament. We believed we were at the very centre of this stellar congregation, a profound but incorrect assumption of our own importance. It was only in the early 20th century that the astronomer Harlow Shapley, by studying clusters of ancient stars, triangulated our true position. He discovered we were relegated to the galactic hinterlands, 30,000 light-years from the core. The revelation was a Copernican demotion on a galactic scale. We were not the centre of the universe, nor of our solar system, nor even of our own island of stars. We were simply part of it, a resident of its sprawling, luminous expanse. Now, let our conceptual vessel drift towards the heart of this magnificent structure. The density of luminaries increases exponentially. Stars are no longer isolated points, but a blazing, continuous fog of light. The galactic core is a chaotic and spectacular place, a crucible of stellar birth and death. And at its very nucleus, veiled by impenetrable clouds of dust and gas, lies a monster. Sagittarius, a star, a supermassive black hole, a gravitational singularity 4 million times the mass of our Sun. It is the silent, unseen anchor around which our entire galaxy revolves. Every star, every planet, every being caught in its slow, inexorable gravitational waltz. This cosmic engine, this point of infinite density, is the quiet ruler of our stellar home. But the Milky Way is not alone in the dark. It is part of a local community. To see it, we must leave our home galaxy behind entirely. We accelerate our perception outwards, the spiral arms of our home shrinking behind us. It becomes a beautiful spinning pinwheel, then a bright smudge, and finally just another point of light. The scale of our journey has now shifted from the interstellar to the intergalactic. The emptiness between these islands of light is of a different order of magnitude. This is the true void, a chasm millions of light-years across. Our first destination is 2.5 million light-years away. The light we're about to intercept from this celestial city began its journey when our earliest human ancestors were first walking the Earth. As we approach, a faint oval of light grows, resolves, and then utterly fills our view. This is Messier 31. The Andromeda Galaxy, our nearest major galactic neighbour and in many ways our cosmic twin. It is a behemoth, larger and more massive than the Milky Way. It contains perhaps 1 trillion suns, a sprawling spiral twice the diameter of our own. If our sky were dark enough, Andromeda would be visible to the naked eye as a hazy patch of light. A whole other universe of stars hiding in plain sight. Observing Andromeda's light reveals a peculiar and startling fact. Unlike almost every other distant galaxy, its light is not stretched and reddened by the expansion of the universe. Instead, its light is compressed, shifted towards the blue end of the spectrum. This is the unmistakable signature of an object moving towards us. Andromeda is not receding, it is on a collision course, hurtling through the void at 110 kilometers per second. This is not a cataclysm to fear, it is a destiny to marvel at. Imagine 2 vast clouds of smoke, each billions of times larger than a solar system, slowly drifting towards one another. This is the nature of a galactic merger. In about 4.5 billion years, the Milky Way and Andromeda will begin their celestial dance. Their outer arms will first interpenetrate, tidal forces flinging great streams of stars and gas into intergalactic space. The galaxies will pass through one another, largely unharmed at the stellar level. The space between individual stars is so immense that direct collisions will be extraordinarily rare. But gravity is relentless. They will slow, turn, and fall back together again. Over hundreds of millions of years they will merge, their supermassive black holes spiralling towards each other at the centre. Eventually a new, single, gargantuan elliptical galaxy will be born from the union, a cosmic entity some astronomers have already named Milkomeda. We are witnessing, in the approaching light of Andromeda, the ghost of our own galaxy's far-flung future. But our local group, this small cluster of gravitationally bound galaxies, contains more than just 2 giants. We turn our attention to the third largest member, the Triangulum Galaxy. At 3 million light-years away, it's a beautiful face-on spiral. Unlike the tightly wound arms of Andromeda, Triangulums are loose and clumpy. It is a gallery of stellar nurseries, vast pink clouds of glowing hydrogen where new suns are being forged. It is a more leisurely, less crowded version of our own home. And then there are the dwarves, the humble satellites that orbit the larger galaxies like moths around a flame. The Large and Small Magellanic Clouds are the most famous of these. Visible from Earth's southern hemisphere, they are not spirals or ellipticals. They are classified as irregular galaxies, chaotic, misshapen collections of stars and gas. Their disorganized appearance is a scar, a testament to the gravitational bullying they've endured from the much larger Milky Way. Our galaxy's gravity has torn at their structures, pulling out long ribbons of gas called the Magellanic Stream. These smaller congregations are being slowly cannibalized, their substance gradually incorporated into our own. Galactic evolution, it turns out, is not a peaceful affair. It is a story of consumption, merger, and gravitational dominance. Having explored our immediate cosmic family, we must now pull back even further. The local group itself is just a tiny, insignificant hamlet on the outskirts of a much larger structure. Our next destination requires a leap of 54 million light-years. We're heading for the heart of our supercluster, a colossal gathering of thousands of galaxies. This is the Virgo cluster. If the local group was a quiet suburban street, the Virgo cluster is the bustling, chaotic core of a cosmic megalopolis. The view here is staggering. The sky is no longer mostly empty. Every direction reveals galaxies of every shape and size. Pinwheel spirals, glowing elliptical orbs, and distorted irregulars litter the void. They are packed together, a swarm of island universes caught in a shared gravitational field. At the centre of this immense congregation are not spirals like our own, but something far older and more massive. Here, the dominant galactic form is the elliptical. Let us approach the king of this realm, the galaxy Messier 87. M87 is a monster. It is a featureless spherical swarm of trillions of ancient yellowed stars. It lacks the beautiful spiral arms and vibrant star-forming regions of the Milky Way. It is an old galaxy, a cosmic giant that has grown to its current size by devouring hundreds of smaller rivals over billions of years. Its stars no longer move in an orderly rotating disk. Instead, they swarm like a hive of bees in chaotic individual orbits around the galactic centre. It is a city of the old, a quiet, settled behemoth. But at its heart, M87 harbours a secret of unimaginable violence. Here lies one of the most massive black holes ever discovered. A gravitational titan 6.5 billion times the mass of our Sun. This is a leviathan so enormous that our entire solar system would fit comfortably within its event horizon. And in 2019, for the first time in history, humanity saw it. Not the black hole itself, for nothing can escape its grasp, not even light. But we saw its shadow, its silhouette against the swirling, superheated disk of matter falling into it. The Event Horizon Telescope, an array of radio dishes spread across our planet, combined to form an Earth-sized virtual lens. They captured a ghostly ring of light, a final, fiery scream from matter at the point of no return. This image was more than a scientific breakthrough. It was a philosophical milestone. We had stared into the abyss, the physical manifestation of a gravitational endpoint, and it stared back. And this black hole is not idle. It is a cosmic engine. As matter spirals inwards, immense magnetic fields channel some of the energy into two colossal jets. These jets, composed of particles accelerated to nearly the speed of light, erupt from the poles of the black hole. One of them in M87 blasts outwards for 5,000 light-years. It is a beam of raw power, a testament to the extraordinary physics at play in the universe's most extreme environments. This single, luminous spear is a structure larger than many entire dwarf galaxies. It is a stark reminder that even in an ancient, seemingly placid galaxy, there are forces at work that defy our terrestrial comprehension. The sheer variety of galaxies in the Virgo cluster forces us to confront a fundamental question. Why are they so different? Why the elegant spirals, the bloated ellipticals, the messy irregulars? This was the question that obsessed the astronomer Edwin Hubble in the 1920s. Working at the Mount Wilson Observatory, Hubble was the first to prove that these spiral nebulae were in fact distant galaxies, island universes just like our own. This discovery fundamentally redefined the size and scope of our reality. He then created a classification system, a way of imposing order on this cosmic zoo which we still use today. It is called the Hubble tuning fork diagram. Imagine the handle of a tuning fork representing the elliptical galaxies. They are graded from E0, which are almost perfectly spherical, to E7, which are highly elongated and flattened. These are the elder states galaxies of the universe, filled with old red stars and little free gas for new star formation. They are often found at the crowded centres of galaxy clusters, the products of numerous mergers. M87 is a pristine example of a giant elliptical. At the point where the handle splits, Hubble placed the lenticular galaxies. These are an intermediate form possessing a central bulge and a disk, but with no discernible spiral arms. They are like spirals that have used up all their gas, their star-forming days long behind them. The beautiful Sombrero Galaxy is a classic lenticular, its bright core bisected by a dramatic dark lane of cosmic dust. The two tines of the tuning fork represent the spiral galaxies. One tine is for standard spirals like Andromeda, classified based on how tightly their arms are wound. The other tine is for barred spirals, like our own Milky Way, which have a bright linear bar of stars crossing their centre, from which the arms emerge. These spiral galaxies are dynamic, active places. Their arms are density waves, cosmic traffic jams where gas clouds are compressed, triggering furious bursts of starbirth. The bluish tint of the arms comes from the brilliant, hot young stars that live fast and die young. To witness this in its full glory, we can journey 30 million light-years to Messier 51, the Whirlpool Galaxy. Here, a large spiral is locked in a gravitational embrace with a smaller companion. The interaction has enhanced and defined the spiral structure, making it one of the most photogenic objects in the cosmos. And what of those that fit nowhere on this elegant diagram? Hubble simply called them irregulars. These are the rebels and refugees of the cosmic order, galaxies like the Magellanic Clouds, their shapes torn and distorted by gravitational interactions with larger neighbours, or the antennae galaxies, a spectacular train wreck of two colliding spirals, their structures thrown into disarray, triggering a firestorm of star formation. Hubble initially thought his diagram might be an evolutionary sequence, that ellipticals slowly flattened and grew arms to become spirals. We now know the opposite is more likely true. The great river of cosmic evolution flows from spirals towards ellipticals. When spirals merge, their delicate disk structures are destroyed, and their stars are scattered into the randomized spherical orbits characteristic of an elliptical galaxy. The tuning fork is not a timeline of a single galaxy's life, but a catalogue of the diverse outcomes of billions of years of cosmic history. Our journey has so far taken us through space, but with every light year we traverse, we are also travelling through time. The light from M87 is 54 million years old, the light from Andromeda 2.5 million. We are not seeing these galaxies as they are now, we are seeing them as they once were. Light is a time machine, and now we are going to push this machine to its absolute limit. We are adjusting our perceptual vessel to look deeper into the cosmos than ever before. We are targeting a tiny, unremarkable patch of sky, an area so small it would be covered by a grain of sand held at arm's length. In 1995, the Hubble Space Telescope stared at such a patch for 10 consecutive days. What it revealed changed cosmology forever, the Hubble Deep Field. The image was not empty, it was filled with 3,000 galaxies. Some were recognisable spirals and ellipticals, but they were smaller, stranger. And some were faint, red, misshapen smudges, the oldest things ever seen. Now, with the power of the James Webb Space Telescope, we can see even further, even deeper into the dawn of time. We are travelling now not millions but billions of light years, 13 billion years into the past. We are looking at the universe when it was less than a billion years old, a cosmic infant. The galaxies here are not the grand, well-ordered structures we have seen so far. They are small, clumpy, and intensely bright with the fire of creation. These are the first protogalaxies, the building blocks of everything that would come later. They are chaotic knots of gas and dark matter, collapsing under their own gravity and igniting in spectacular bursts of star formation. The light from these nascent stellar cities is so ancient, so stretched by the 13 billion year expansion of space-time, that it has been shifted far beyond the visible spectrum into the infrared. Webb, with its golden mirrors and infrared eyes, is built to capture these primeval ghosts. Looking at these images is an experience that borders on the spiritual. Each faint red dot is a congregation of millions of the universe's very first suns. We are witnessing the moment the cosmos first lit up, the end of the cosmic dark ages. The light from these galaxies is older than our planet, older than our sun. It was already halfway through its immense journey to us when the Earth was still a molten ball of rock. We are seeing the seeds from which all subsequent cosmic structure, including our own Milky Way, would eventually grow. It is a humbling, profound connection to our deepest cosmic origins. We are seeing our own galactic ancestry. Throughout this entire extraordinary voyage, we have focused on the light, the brilliant stars, the glowing nebulae, the assembled majesty of the galaxies. But we have been ignoring the vast majority of the universe, because the vast majority of the universe is invisible. As we look at a cluster of galaxies like the Virgo, we can measure how fast the outer galaxies are moving. When we do, we find something deeply unsettling. They are moving far too quickly. Based on the mass of all the stars and gas we can see, the cluster should not have enough gravity to hold itself together. These speeding galaxies should have flown off into the void billions of years ago. The only way the cluster can remain bound is if there is more mass. A lot more mass. About 5 times more mass than everything we can see combined. This mysterious, invisible substance is what astronomers have named dark matter. It does not shine, it does not reflect light, it does not interact with ordinary matter in any way except through gravity. It is a transparent, ethereal scaffold upon which the visible universe is built. Imagine a sprawling city at night, seen from high above. You can see the bright lights of the buildings, the streets, the cars, but you cannot see the dark steel girders, the concrete foundations, or the asphalt roads that give the city its structure. Luminous matter, the stars and galaxies, are just the lights. Dark matter is the invisible architecture of the cosmos. It was the gravitational seeds around which the first protogalaxies collapsed. It is the unseen halo that envelops our own Milky Way, holding our spinning disk together. We don't know what it is. It may be a new type of subatomic particle, one that physicists are desperately hunting for in deep underground laboratories. For now, it remains the great ghost of the cosmos, its presence felt everywhere, but its nature a profound enigma. And the universe holds one final, even deeper mystery. In the late 1990s, two independent teams of astronomers were using distant supernovae to measure the expansion rate of the universe. They expected to find that the expansion was slowing down, pulled back by the gravity of all the matter, both light and dark. They found the exact opposite. The expansion of the universe is accelerating. Something is pushing everything apart. A mysterious pressure is embedded in the fabric of space-time itself. This unknown force has been given a name as mysterious as its nature: dark energy. If dark matter is the cosmic scaffold holding things together, dark energy is the cosmic force pushing them apart, and it is winning. It makes up nearly 70% of the total energy density of the universe. Ordinary matter, everything we have ever seen or touched, every star, every galaxy, is less than 5% of the cosmic inventory. We are adrift in a universe whose fundamental composition and ultimate fate are dominated by forces we do not comprehend. This accelerating expansion paints a somber picture of the far future. As space itself expands faster and faster, galaxies will be pushed away from us. Eventually, they will recede at speeds faster than light itself. Their light will never be able to reach us. One by one, the galaxies will disappear from our sky. First the Virgo cluster, then Andromeda, until only our own local group remains. And in the unimaginably distant future, even those will merge into the single entity of Milkomeda. An observer in that far-flung era will look out into a sky that is utterly, completely empty. They will see their own island universe, but nothing beyond. They will live in a state of cosmic solitude, with no evidence that other galaxies ever existed. The magnificent populated cosmos we see today is a fleeting, temporary phase. We are privileged to live in a golden age of cosmology, a time when the universe's story is still visible to us. Our journey must now come to an end. We retract our perception, pulling back from the edge of creation, past the great clusters and superclusters. We fly past the ghostly ellipses and the vibrant spirals. We cross the 2.5 million light-year gulf back to our own local group. And there, ahead of us, is a familiar, comforting sight: the swirling arms of the Milky Way. We plunge back into its disk, through the Orion arm, and towards a single yellow-white star, our Sun. And around it, a small blue marble, vibrant with water and life, Earth. We have returned home, but we are not the same. We have seen the sheer scale of the stage on which our small human drama unfolds. Every point of light in our sky is a sun. Every faint smudge is a city of 100 billion suns. And there are perhaps 2 trillion of these cities in the observable universe. The numbers are meaningless, they are poetry. They speak of a creation more vast, more varied, and more mysterious than our minds can fully contain. Our journey was not through every single galaxy. That would be impossible. It was a journey through every kind, a voyage to understand our place in the grand cosmic tapestry. We are the products of this universe. The iron in our blood was forged in the heart of a dying star. The calcium in our bones was created in a supernova explosion. We are, in the most literal sense, stardust. And for a brief moment in the immense timeline of the cosmos, that stardust has woken up. It has built telescopes and spacecraft. It has learned to read the ancient light from the dawn of time. We are the universe's way of knowing itself, and the journey of discovery, the voyage through the great and beautiful darkness, has only just begun. What if there was a world you felt you knew a place etched in some ancestral memory of Earth? A world sculpted by rain wind and the patient flow of liquid over millennia, carving canyons and pooling into vast placid seas that glitter under a shrouded sky. You can almost feel the dampness in the air, the grit of sand dunes shaped by patient breezes. This landscape of river deltas and shorelines is so profoundly familiar, it feels like a dream of home. But this is no dream, and it is most certainly not home. It's a place where every comforting similarity is a deception, a cosmic mirage that masks a truth so profoundly alien, it forces us to question the very nature of a world. This is a moon that has forgotten. It is a moon, a celestial body that wraps itself in the majestic trappings of a planet, performing a perfect chilling impression of Earth in a theatre of unimaginable cold. Suspended in the profound blackness of the outer solar system orbiting the colossal ringed sovereign Saturn is Titan. It is not some barren pockmarked rock like our own moon, a silent testament to ancient impacts. Instead, Titan presents an enigmatic, featureless face to the cosmos, a perfect hazy orange sphere. For centuries it was little more than a pinprick of light, a mystery wrapped in an impenetrable atmospheric cloak. Its true nature remained locked away, hidden beneath a perpetual smog of organic molecules, a veil so thick it denies us any glimpse of the surface below. What could possibly lie beneath such a persistent planet-wide shroud? What geologic dramas and atmospheric secrets could justify such an immense and complex atmosphere, one denser and more massive than our own? This isn't just a thin exosphere clinging to a dead rock. It is a dynamic, churning weather engine, a chemical factory on a planetary scale. For us creatures born of water and sunlight, the very idea of this place is a paradox. It possesses all the machinery of a living world. Weather systems rage, clouds gather and disperse, and rain falls from the sky to feed meandering rivers that flow into great lakes and seas. There are seasons here driven by the long, slow 30-year orbit of its parent planet Saturn. A year on Titan is a vast, ponderous epic where summer and winter are each drawn out for more than 7 Earth years. But this Earth-like behaviour is a cruel trick of chemistry. The air you would try to breathe is a suffocating blend of nitrogen and methane utterly devoid of free oxygen. The temperature at the surface plummets to a staggering 290 degrees below 0 Fahrenheit, a cold so absolute it turns water into a substance as hard and unyielding as granite. On Titan, water is not the solvent of life. It is the bedrock of the entire world. The mountains are made of ice. The pebbles on the shoreline are frozen lumps of H2O polished smooth by a liquid that is not and could never be water. Imagine standing on that alien shore. The sky above is not blue but a dim perpetual orange twilight, the colour of a dying campfire filtered through the thick organic haze. The gentle lapping you hear against the frozen shore is not the comforting sound of water. It is the whisper of liquid methane and ethane hydrocarbons that we use on Earth as rocket fuel and industrial chemicals. Here in this cryogenic realm they are the stuff of oceans. A storm on the horizon would not be a cleansing downpour of life-giving water, but a deluge of frigid, flammable methane, a rain that would flash freeze and burn you simultaneously. This is the fundamental mind-altering truth of Titan. It is a dark mirror to Earth, a planet where the roles of rock and water have been terrifyingly reversed. It is a world built from the very same elements that gave rise to us carbon and hydrogen, but twisted by the brutal cold into a chemical landscape that defies our terrestrial intuition. For decades, we could only speculate, piecing together clues from faint spectral readings and fleeting flybys. Then in 2005, humanity finally pierced the veil. The Huygens probe, a tiny intrepid emissary from Earth, detached from the Cassini orbiter and began its final terrifying plunge into the unknown. For 2.5 hours it fell through the orange smog, tumbling through nitrogen skies, buffeted by winds we never knew existed. Its instruments, waking up in the heart of the alien atmosphere, began to taste the air, to measure the pressure, to listen for the distant crackle of lightning that never came. As it descended through the final layers of haze, its cameras opened their eyes upon a world no human had ever seen. There unfolding below was the impossible, a landscape of drainage channels, of highlands and lowlands, a world that looked as if it had been photographed from an airplane window, flying over a coastline on Earth. The probe touched down not with a crash, but with a dull, gentle thud. It had landed in something soft, a material with the consistency of wet sand. For a precious 72 minutes before its batteries died, and it was frozen into eternal silence, Huygens transmitted a postcard from another world. It showed us a floodplain littered with rounded water ice pebbles, a landscape scoured and shaped by the flow of liquid methane. It was a moment that changed everything, transforming Titan from an abstract point of light into a tangible place, a place we could map, a place we could almost understand. We had landed on the shores of a methane riverbed, on a world nearly 1 billion miles from the Sun. The sheer audacity of the achievement was matched only by the depth of the mysteries it uncovered. This world, born from the same protoplanetary disk as Earth, is a stunning example of convergent evolution on a planetary scale. Just as unrelated species on Earth can evolve similar body plans to solve similar problems, Titan has developed Earth-like geologic features using a completely different chemical toolkit. Its planetary engine, driven by the faint warmth of its interior and the feeble light of a distant sun, follows the same physical laws as our own. Liquid seeks its own level, carving paths of least resistance on its journey to the sea. Wind erodes and deposits sediment, building vast fields of organic sand dunes that encircle the equator. There may even be volcanoes, but they would be cryovolcanoes, mountains that erupt not with molten rock, but with a slushy, viscous slurry of water and ammonia from the moon's warmer interior. It is a complete functioning geologic system, a simulacrum of Earth, operating at a temperature where our biology would instantly shatter. And yet it is precisely this extreme environment, this crucible of cold and chemistry, that gives birth to the most tantalizing and audacious question we have ever asked of another world. We see the elements carbon and hydrogen in abundance. They form the methane in the air, the ethane in the seas, and the complex organic gunk that constantly rains down from the upper atmosphere, coating the surface in a dark, sticky residue. These are the building blocks of life as we know it, the fundamental components of amino acids, proteins, and DNA. On Earth, under the gentle influence of liquid water, these ingredients assembled into biology. But what happens to these same ingredients on Titan? What is their ultimate fate in a world of crushing pressures and cryogenic temperatures, where the chemical rules are rewritten? The journey begins high above the surface, in the tenuous outer reaches of Titan's atmosphere. Here, sunlight, though 100 times weaker than at Earth, is still energetic enough to be a powerful catalyst for change. Ultraviolet rays and charged particles from Saturn's magnetic field crash into the methane molecules, which are simple structures of one carbon atom bonded to 4 hydrogen atoms. This cosmic bombardment is a relentless act of molecular violence. It shatters the stable methane bonds, breaking the molecules apart. The fragments, the freed carbon and hydrogen atoms, do not simply linger. In the cold, dense environment, they frantically seek new partners, recombining into ever more complex and heavy hydrocarbons. They form chains and rings, creating a rich organic smog of molecules like acetylene, propane, and benzene. This process creates the very haze that shrouds the moon, a constant gentle snowfall of complex organic material known as tholins. Over billions of years, this slow, persistent drizzle from the sky has coated the entire surface, burying the primordial water ice crust under a deep blanket of organic sediment. This material is in a very real sense the raw, uncooked stuff of life preserved in a deep freeze. But this is only the beginning of the story, the first act in a far more dramatic chemical play. This process loads the atmosphere with carbon. And what happens next, deep within the churning troposphere, leads us to a stunning, almost unbelievable hypothesis. It leads us to a possibility born from the laws of high-pressure physics, a conclusion that sounds like it was torn from the pages of mythology. What if the conditions on Titan are so extreme, so utterly alien, that they could force carbon to perform its most spectacular transformation? In the deepest layers of its atmosphere, thousands of miles down, the pressure becomes immense, thousands of times greater than at sea level on Earth. The temperature also rises not from sunlight, but from the sheer compressive force of the atmospheric column. Here, in this natural high-pressure laboratory, the methane molecule is subjected to forces it cannot withstand. The immense pressure could squeeze the hydrogen atoms completely away from the carbon-liberating pure elemental carbon in the heart of a methane storm, and carbon under such extraordinary pressure has only one stable form it can take. It crystallizes. It transforms into its hardest, most stable, most brilliant allotrope. It becomes diamond. Could it be that on this bizarre frozen echo of Earth it rains diamonds, not the diamonds we know forged from heat and pressure deep within our planet's mantle? These would be something else entirely, methane-derived diamonds born not of geology, but of meteorology. Imagine a storm cloud gathering in the orange gloom, a storm not of water, but of super-pressurized, super-cooled liquid methane. As the storm builds, the pressure inside intensifies, squeezing the methane molecules past their breaking point. The storm would not release rain, but a shimmering crystalline sleet of microscopic diamonds, each one a testament to the extreme physics of this world. These celestial jewels, heavier than the surrounding atmosphere, would begin to fall. They would descend through the thick nitrogen-rich air for thousands of miles, a slow, silent, glittering rain that might last for centuries. What would happen to them? Would they accumulate on the surface, creating sparkling beaches of diamond dust along the shores of the methane seas? Or would they continue their journey downward, sinking through the liquid, ethane and methane of the oceans, settling into a deep crystalline layer on the alien seabed? The physics suggests that upon reaching the warmer core of the Moon, these diamonds would likely melt back into a sea of liquid carbon, perpetuating a cycle of unimaginable scale and grandeur, a global hydrocarbon diamond cycle that has been operating for eons. The very concept is staggering, a form of weather so exotic it borders on the fantastical. Yet it is a scientifically plausible hypothesis, a direct consequence of the chemistry and conditions we know to exist on this incredible moon. This is the central mystery of Titan, the question that elevates it from a mere scientific curiosity to an object of profound philosophical importance. It challenges our most fundamental assumptions about how worlds work. It presents us with a place that forces us to expand our imagination, to consider possibilities that we had previously relegated to science fiction. The prospect of diamond rain is not just a geological spectacle, it is a signpost. It points to the incredible diversity of planetary processes in our universe, showing us that the familiar cycles of Earth are but one possible outcome in an infinitely creative cosmos. The universe, it seems, has more ways of building a world than we have ever dreamed. And so our journey begins. We must now become scientific detectives, peeling back the layers of this world one by one, from the highest reaches of its smog-filled skies to the unknown depths of its hydrocarbon oceans. We will follow the path of the carbon atom from a simple gas to a complex organic molecule, and perhaps to a falling crystal of pure diamond. We will investigate the evidence, study the atmospheric models, and explore the physics that could make such an incredible phenomenon possible. The story of Titan is not just about a moon. It is about the limits of chemistry, the nature of planetary evolution, and the search for our own place in a universe that is proving to be more strange, more beautiful, and more surprising than we could ever have imagined. The orange haze beckons, and beneath it lies a world of dark oceans, frozen mountains, and a sky that may hold the most extravagant storms in the entire solar system. Of all the worlds we have ever known, why did we become so obsessed with one we could not even see? In the grand celestial theatre of our solar system, with its burning suns and cratered wanderers, there are countless spectacles to command our attention. Yet for generations our gaze was drawn back again and again to a tiny, featureless orange dot, adrift in the outer darkness. It was a world that promised everything and showed us nothing. This cosmic enigma, a moon larger than the planet Mercury, orbits the magnificent ringed giant Saturn. We call it Titan, and its story is not one of easy discovery, but of a relentless centuries-long quest to peer through an impossible veil. It begins not with a clear view, but with a profound and tantalizing frustration. When the Dutch astronomer Cassini-Huygens first resolved that faint point of light in 1655, he had no idea of the paradox he had uncovered. To him, and the astronomers who followed it, was simply another satellite, a loyal companion to Saturn, dutifully tracing its path through the heavens. For nearly 300 years, that is all it remained, a name in a catalogue of predictable gravitational clockwork. The technology of the time, the finest brass and glass, could reveal the swirling storms of Jupiter and the majestic architecture of Saturn's rings, but Titan stubbornly refused to give up its secrets. It was just a smudge of light, a frustratingly blank canvas. The first hint that something was deeply strange, something utterly unique in the known universe, didn't arrive until 1944. It came not as an image, but as a ghost in the machine. The astronomer Gerard Kuiper, using a spectrometer at the McDonald Observatory in Texas, did something revolutionary. He wasn't just looking at Titan, he was listening to its light. He passed the faint reflected sunlight from the moon through a prism, shattering it into its constituent colours, a rainbow spectrum. And within that spectrum he saw what no one had ever seen from a moon before: dark lines, gaps in the light, the unmistakable spectral fingerprints of molecules. These were absorption bands, specific frequencies of light that had been swallowed by a gas. The culprit was methane. This single ghostly signature transformed Titan overnight from a dead rocky satellite into a world of profound mystery. Rock and ice do not hold on to gas. To have an atmosphere, a world needs a powerful gravitational pull and a magnetic field to fend off the solar wind. Moons weren't supposed to have them. Our own moon is a silent, airless wasteland. Jupiter's great moons, Io, Europa, Ganymede and Callisto, are either airless or possess atmospheres so thin they are barely whispers. Yet Titan, orbiting 1 billion miles from the Sun, was cloaked in a substantial gaseous envelope. It was an impossibility, a celestial rule-breaker. This discovery ignited a firestorm of questions that would smoulder for decades. What was this atmosphere made of? How thick was it? And the most tantalizing question of all, if there was an atmosphere, what lay beneath it? The presence of methane was itself a deep riddle. Methane is a fragile molecule. In the upper reaches of an atmosphere under the relentless bombardment of ultraviolet light from the sun, it should be destroyed, broken apart, and reformed into more complex compounds in a cosmic flicker, geologically speaking. For it to still be present in such abundance meant something had to be actively replenishing it. Some process, some form of geology or chemistry, had to be cycling methane back into the sky. Titan, it seemed, was not a dead world, but a dynamic, active one churning with processes we couldn't begin to imagine. The blank orange disk was no longer just a curiosity. It was a challenge, a gauntlet thrown down to human ingenuity. The mid-20th century was the dawn of a new age of exploration. We were no longer merely observers of the heavens, we were becoming participants. Our rockets born from the crucible of conflict were now being pointed outwards, carrying our ambitions into the void. This was the era of the Grand Tour, a once-in-a-lifetime planetary alignment in the late 1970s that would allow a single spacecraft to visit all 4 of the outer gas giants. This audacious plan gave birth to the twin Voyager probes, our first robotic emissaries to the realm of Saturn. Their primary mission was to study the gas giants themselves and their spectacular rings, but for a small group of planetary scientists, Titan was the secret coveted prize. Here was our first real chance to get an up-close look, to finally see what lay beneath the haze. The anticipation within the scientific community was electric. Years of speculation of piecing together clues from faint slivers of light were about to be put to the test. As Voyager 1 made its historic flyby of Saturn in November 1980, it was programmed to make a dramatic sacrifice. It would use the giant planet's gravity not to continue its tour of the outer system, but to divert from its path, to make a sharp turn for a close encounter with Titan. This maneuver would permanently fling the probe out of the plane of the solar system, ending its planetary mission. The data from Titan was deemed that important. It was a one-shot opportunity and the world held its breath. The first images that trickled back to Earth were stunning in their resolution, showing a perfectly spherical, featureless, hazy orange ball. The probe's cameras operating in the visible spectrum of light were utterly defeated. The haze was even thicker, more impenetrable than anyone had feared. There were no breaks in the clouds, no mountain peaks poking through, no glint of a distant sea. Just an endless, uniform tangerine-coloured smog. For the public, it was an anticlimax. For the scientists, it was a moment of profound, crushing disappointment mixed with a jolt of electrifying discovery. We couldn't see the surface, but Voyager's other instruments were screaming with data. It had plunged through the upper atmosphere, tasting its composition, measuring its temperature and pressure. The results were staggering. The atmosphere was not a thin veneer, but a thick, soupy ocean of gas. The pressure at the surface, they calculated, was 50% greater than that of Earth's at sea level. You could walk around on Titan if you could survive the cold without a pressure suit. The primary component was not methane, as some had suspected, but nitrogen, just like Earth's. Nitrogen, the stable foundational gas of our own world, made up more than 95% of Titan's air. Suddenly, this alien moon started to look eerily familiar. It was the only other body in the entire solar system, with a dense nitrogen-rich atmosphere. We had found a twisted sibling to our own planet, a parallel Earth preserved in a deep freeze, and the chemistry was even more bizarre. Voyager's sensors detected a whole zoo of complex organic molecules in the upper atmosphere. Ethane, acetylene, propane, hydrogen, cyanide. These weren't just simple gases. They were hydrocarbons, the fundamental building blocks of life as we know it. The very same ultraviolet light that destroyed methane was, it turned out, the engine of a vast world-spanning organic chemical factory. The broken pieces of methane were reassembling themselves into ever more complex chains, creating a thick photochemical smog that rained down continuously from the sky. This constant drizzle of organic material, this unending shower of thiolins, as Carl Sagan would later dub them, had likely been coating the surface for billions of years. Titan wasn't just a world with an atmosphere, it was a planetary-scale laboratory for prebiotic chemistry. It was a place where the steps that may have led to life on Earth were happening right now, frozen in time by the unimaginable cold. The moon we couldn't see had suddenly become the most important place to look for clues about our own origins. The tantalizing failure of Voyager 1's cameras galvanized the scientific community. The frustration of being denied a view of the surface only deepened the mystery and strengthened their resolve. We now knew the stage was set for something incredible. We had a thick nitrogen atmosphere complex of organic chemistry, and a constant rain of the building blocks of life. But what was the landscape like beneath that orange sky? What form did this organic material take once it reached the ground? Did it pile up in vast black hydrocarbon dunes? Did it dissolve in some unseen liquid? The fundamental missing piece of the puzzle was the question of liquid. On Earth, our weather, our geology, our very biology is dominated by the water cycle: evaporation, condensation, rain rivers, lakes and oceans. What was the equivalent cycle on Titan? The answer scientists theorized lay with the very methane that started the mystery. At Titan's surface, temperatures are mind-numbing minus 180 degrees Celsius water is frozen as hard as granite. It forms the bedrock of the world. But methane, the gas we burn in our stoves, behaves in a completely different way in that extreme cold. It can exist as a liquid. This was the birth of a revolutionary and poetic idea that on Titan methane could play the role that water plays on Earth. Could there be methane clouds? Could it rain methane from the sky? Could that rain carve rivers into the landscape pool, into vast lakes, or even fill entire oceans of liquid and natural gas? We were contemplating a world with a weather cycle based on hydrocarbons. A place where you might see a shoreline not of sand and water, but of frozen water ice and liquid methane. It was a vision straight out of science fiction, but every piece of data we had pointed toward its possibility. The questions became more focused, more urgent. What was the source of the methane that was replenishing the atmosphere? Could it be cryovolcanism, volcanoes that erupt not with molten rock, but with a frigid slurry of water, ice and ammonia, venting methane from a subterranean ocean? Or was the methane simply evaporating from vast surface seas, completing a grand planet-wide hydrocarbon cycle? And if these lakes or seas existed, what other complex chemistry might be occurring within their depths? In a liquid solvent, even one as strange as methane organic molecules could mix, interact and build up into even more complex structures over geological timescales. The implications were breathtaking. We had to go back. We had to do more than just a fleeting flyby. We needed to settle into orbit Titan for years to map its hidden face with tools that could pierce the haze. And more than that, we had to do the unthinkable. We had to land. This grand ambition required a technological leap far beyond Voyager. It meant designing a spacecraft that could not only survive the decade-long journey to Saturn, but could also carry its own dedicated lander. We needed radar and instrument that could use radio waves to paint a picture of the surface topography ignoring the smog completely. We needed infrared cameras that could peer through specific windows in the atmospheric haze where light could just barely squeak through. And we needed a probe, a heat-shielded, parachute-equipped vessel of discovery that could survive a fiery atmospheric entry and a descent of over 2 hours through the alien sky, sending back data all the way down. The mission that grew from these audacious dreams would be called Cassini-Huygens, a joint venture between NASA and the European Space Agency. It was one of the most complex and ambitious robotic exploration missions ever conceived. It was our answer to the challenge that Titan had presented. The years of planning were filled with debate, with engineering marvels, and with a relentless sense of purpose. Scientists argued over instrument designs, engineers battled the laws of physics and budget constraints, and an entire generation of researchers dedicated their careers to answering the questions that Voyager had left hanging in the void. What is the true nature of this world? Is it a frozen static relic of the early solar system, or is it a dynamic, living place in its own right? What secrets are written in the organic sludge that has rained down for eons? Does a world without liquid water, a world of liquid methane, have the potential for life? Not life as we know it, but some other stranger form born from a different chemistry under an orange sky. These were the fundamental drivers, the core of the obsession. The need to know what was happening on the ground of that shrouded world became a defining goal for planetary science. Titan had established itself as more than just a moon. It was a cosmic time capsule, a foggy mirror reflecting a distorted image of our own planet's infancy. To understand Titan was to potentially understand the prerequisite conditions for life anywhere in the universe. It was a control experiment on a planetary scale. By sending a sophisticated emissary to this distant realm, we were not just exploring another world, we were embarking on a journey back into our own deepest past, searching for the lost chemical pathways that transformed a sterile rock into a living biosphere. The tantalizing hints we'd gathered from afar had woven a spell of irresistible curiosity. We had followed the breadcrumbs of light, we had decoded the chemical ghosts in its atmosphere, and now we were ready to finally physically breach the gates of this forbidden kingdom and lay its secrets bare. The stage was set for our return. After a silent 7-year pilgrimage across the void, a journey spanning billions of kilometers, and weathering the lonely vacuum between worlds, humanity's most ambitious emissary finally reached its kingdom. The Cassini-Huygens spacecraft, a marvel of engineering and a vessel for our collective curiosity, gracefully surrendered to the immense gravity of Saturn, firing its engines to become an artificial moon of the great ringed planet. Its primary quest, the obsession that had driven its creators for decades, was not the magnificent planet itself, but its largest, most enigmatic moon. What had for centuries been a mere point of light, a frustratingly opaque orange marble that guarded its secrets with an impenetrable atmospheric shroud, was now a world waiting to be mapped, a mystery poised for its grand unveiling. The veil was about to be torn away. The first approaches were cautious, a series of carefully choreographed flybys. Cassini's instruments, a symphony of sensors and scanners, began their work, but the initial views in visible light only confirmed what we already knew. Titan was a featureless pumpkin-coloured sphere. The thick nitrogen-rich atmosphere, choked with the complex organic smog we call tholins, scattered light so effectively that the surface remained completely hidden, a planetary ghost shrouded in photochemical haze. It was a tantalizing, infuriating dead end. But Cassini carried a secret weapon, an instrument that would allow it to see in the dark, to peer through the unseeable. It carried a sophisticated radar imager, designed not to look, but to listen. It would not be tricked by the smog. It would paint the landscape with radio waves, using their echoes to sculpt a portrait of the unseen world below. The mission controllers held their breath. Years of planning a voyage across the entire solar system all culminated in these moments. The spacecraft's massive antenna dish, which had served as its link to Earth, now swiveled to face Titan. It began to sing an invisible song, sending out pulses of radio energy that sliced through the orange haze as if it weren't even there. These signals struck the surface and bounced back, carrying with them the secrets of the terrain they had touched. On Earth, in the hushed control rooms of the Jet Propulsion Laboratory, these echoes began to resolve into the first ever clear images of Titan's surface, and what they revealed sent a shockwave of disbelief and exhilaration through the entire scientific community. There etched into the frozen ground were features so dark to the radar's eyes, so incredibly flat and smooth, that they could only be one thing: liquids, vast stable bodies of standing liquid. For the first time we were looking at lakes and seas on another world. This wasn't the fleeting hope of water on Mars locked away as polar ice, or buried underground. This was a geography of shorelines, of coastlines, of immense placid surfaces stretching for hundreds of kilometres. The first data strips that came back showed a region near the North Pole, peppered with these dark, telltale patches. Scientists, their voices a mixture of awe and academic rigour, began giving them names not of earthly lakes, but of mythical sea monsters: Kraken Mare, Laniakea Mare, Punga Mare. The names themselves were an admission that we had crossed a threshold into a new realm of exploration, a world both fantastically alien and hauntingly familiar. Laniakea Mare alone was a vast sea larger than Lake Superior on Earth, a deep, sprawling basin filled not with water, but with liquid hydrocarbons, primarily methane and ethane. This discovery was a revelation that fundamentally altered our conception of worlds. We had always thought of geology and hydrology in terms of rock and water, but here was a planet-sized moon with a geology of frozen water ice as hard as granite, and a hydrology based on compounds that we use on Earth as fuel. Imagine a world where the mountains are made of ice, the bedrock is frozen solid, and the oceans are filled with the liquid equivalent of natural gas. The implications were staggering, forcing planetary scientists to rewrite their textbooks in real time. But the lakes and seas were only the first brushstroke in a far grander masterpiece. As Cassini continued its orbital tour, making dozens of targeted flybys over the years, the radar swaths began to connect, stitching together a global map of this bizarre cryogenic paradise. And with each new pass, the picture grew richer, more complex and more dynamic than anyone had dared to imagine. The radar didn't just show static pools of liquid. It revealed intricate networks of channels flowing into them, unmistakable river valleys carved into the icy terrain. Some were vast, like the Vid Flumina river system, which meandered for over 400 kilometres, before emptying into the northern sea of Laniakea Mare. These were not the faint ancient water channels of Mars. These were active, deeply incised riverbeds, complete with deltas, tributaries and sandbars. They were evidence of a powerful erosive force at work, a fluid that had sculpted the landscape over millennia. We were witnessing a world with a complete functioning hydrological cycle, a perfect analogue to Earth's water cycle, but operating at a chilling -180 degrees Celsius. The sun's faint warmth, even at that immense distance, was just enough to evaporate the liquid methane from the surface of the seas. This methane vapour would then rise form clouds, and eventually condense, falling back to the surface as rain. Methane rain. The idea was once pure science fiction, a fever dream of planetary potential. Cassini's instruments turned it into observed fact. Its cameras captured transient clouds blooming and dissipating over the equatorial regions, and its sensors detected the chemical signature of methane saturation in the atmosphere just before these cloudbursts occurred. We couldn't see the raindrops themselves, but we could see their aftermath. Dark stains would appear on the surface after a storm system passed patches of ground, temporarily darkened by a hydrocarbon downpour, only to dry out and fade over the following days. We were watching the weather on an alien world. We were seeing the geological engine in action, a slow, frigid metabolism powered not by water, but by methane. This single profound discovery that Titan possessed a complex, Earth-like system of weather and geology, built from completely alien materials, posed an existential challenge to our understanding of how worlds work. It demonstrated that the fundamental processes of cloud formation, precipitation, erosion and deposition were not unique to water. They were universal physical principles that could manifest anywhere the conditions were right, using whatever materials were available. Yet even as the orbiter painted its magnificent portrait from above, a crucial piece of the puzzle remained. What was it actually like on the surface? What would you see? What would you feel? The radar could map the geography, but it couldn't tell us about the texture of the ground or the colour of the sky from below. To truly know this world, we had to go there. We had to touch it. This was the second and arguably most daring part of the mission. Riding piggyback on Cassini all the way from Earth was a small disc-shaped probe named Huygens. It was Europe's contribution to the mission, a kamikaze cartographer designed for a one-way 2.5-hour journey into the unknown. On Christmas Day 2004, Cassini gave its companion a gentle push, sending Huygens on its final ballistic trajectory toward the heart of the orange haze. For 3 weeks it coasted silently through space, a message in a bottle aimed at an alien shore. Then came the moment of truth. Huygens slammed into the upper layers of Titan's atmosphere at over 20,000 kilometers per hour. It became a meteor, a fiery spearhead protected by a heat shield that glowed brighter than the distant sun. Within minutes, its velocity was slashed by the thick, soupy air. Parachutes deployed a carefully sequenced ballet of nylon and cords unfolding in the frigid sky. The heat shield was jettisoned, and with it the probe's protective shell fell away, exposing its suite of instruments and its single precious camera to the environment for the first time. For the next 2 hours, Huygens drifted down through the layers of smog, a lonely messenger descending into a world no human eye had ever seen. It tasted the air, measured the winds, and listened for the crackle of distant lightning that never came, and it took pictures. The images it sent back during its descent were among the most dramatic and awe-inspiring in the history of exploration. As it dropped below the thickest layers of haze, a landscape of astonishing complexity resolved into view. We saw bright highlands seemingly made of water ice etched with a dendritic network of dark, spidery drainage channels. It looked like an aerial photograph of a coastline on Earth, a view from an airplane window, yet every feature was sculpted by liquid methane flowing over frozen water. These were the very river systems the orbiter's radar had hinted at, now seen in stunning high-resolution detail. They were real. They were undeniable. The probe continued its descent, the ground rushing up to meet it, revealing a floodplain littered with rounded cobblestone-like objects. Then, with a gentle, resonant thud, Huygens landed. Humanity had arrived on the surface of Titan. The probe survived the impact, continuing to transmit for over an hour from its new home. The data it sent back in those precious minutes was a treasure trove. A penetrometer on its underside measured the consistency of the landing site, finding it to have the texture of wet sand, a thin, solid crust over a softer, damp material. The camera, now just centimetres from the ground, showed us a field of these rounded stones, almost certainly chunks of water ice worn smooth by the flow of liquid over eons. We had landed in a riverbed, an ancient or perhaps seasonally active channel where liquid methane once coursed. The air was still, the light was dim, an eerie twilight about 10 times brighter than the light of a full moon on Earth. And in the distance a horizon of low hills rose against the pale orange sky. We were there. We were standing on a world where it rained gasoline. The combined data from Cassini's orbital reconnaissance and Huygens' ground truth descent painted a holistic, breathtaking picture. Titan was not a dead static ice ball. It was a living world, a dynamic world. It had weather. It had seasons. It had vast shifting dune fields made not of silicate sand but of solid organic particles, hydrocarbons, that had rained from the sky. It had volcanoes, but they were cryovolcanoes spewing not molten rock, but a cold, slushy mixture of water and ammonia from the moon's interior. We had discovered a world that was a dark mirror to our own, a cryogenic carbon copy of Earth's geology, driven by a chemistry so exotic it defied easy categorization. This revelation shattered our comfortable water-centric view of planetary activity. The processes that make Earth a dynamic planet were not, it turned out, exclusive to Earth. Titan showed us that nature is endlessly creative, capable of building a world of stunning complexity using an entirely different chemical toolkit. But in doing so, it opened up a Pandora's box of new, more profound questions. For decades we have equated liquid water with the potential for life. Our search for habitable worlds has been a search for water. Titan, however, presented us with a world that had everything else: a thick atmosphere for protection, a stable liquid medium on its surface, and a constant supply of complex carbon-based organic molecules raining down from its skies. All the ingredients for life as we know it except for the water. The liquid was methane. The temperature was cryogenic. It was a world teeming with the building blocks of biology, but suspended in a solvent that seemed to us utterly inhospitable. Could life arise in such a place? Could a biology exist that is not based on water but on liquid methane? The discovery of Titan's active hydrocarbon-rich environment didn't just give us answers. It confronted us with a question that strikes at the very heart of our search for life in the universe, forcing us to wonder if our own earthly existence is the only template, or merely one possibility among many. But the liquid that scours the canyons and fills the lakes of Titan is not the same simple substance that rises from their surfaces. Something profound happens in the high, thin atmosphere, a form of celestial alchemy that fundamentally alters the moon's chemistry, forever changing the air, the land, and the rain itself. For billions of years, a quiet, relentless process has been underway, a transformation driven not by heat or volcanic fury, but by the faint, cold light of a distant star. Our sun, nearly 1 billion miles away, is a pale disk in Titan's sky, its warmth barely a whisper against the cryogenic chill. Its visible light struggles to pierce the thick orange shroud, leaving the surface in a perpetual haunting twilight. Yet it sends another kind of message across the void, an invisible energetic rain of ultraviolet radiation, a form of light so potent it acts like a microscopic scalpel, slicing apart the very molecules that make up the atmosphere. High above the clouds in the stratosphere where the haze begins to thin, methane molecules drift in the silent frozen expanse, here in this upper sanctuary of the sky, they are vulnerable. A single ultraviolet photon having travelled for over 80 minutes from the sun ends its long journey with a cataclysmic impact on a methane molecule. The energy it carries is perfectly tuned to sever the bonds that hold the molecule's single carbon and 4 hydrogen atoms together. The collision is instantaneous, violent, and profoundly creative. In that flash, the stable, unassuming methane is shattered. A hydrogen atom is ripped away, sent careening into the void. What remains is no longer methane. It is something new, something unstable, and desperately reactive. It is a chemical ghost, a fragment known as a radical, a molecular shard, hungry to restore its own stability. Imagine this happening not once, but trillions upon trillions of times every second across the entire sun-facing hemisphere of Titan. The upper atmosphere becomes a churning sea of these broken pieces, a chaotic soup of highly energized molecular fragments. These are the fundamental building blocks of Titan's great mystery. These reactive radicals born from sunlight and methane do not remain alone for long. They are driven by the fundamental laws of chemistry, to find new partners, to form new bonds, to create larger, more complex structures. A methyl radical, that lonely carbon with its 3 remaining hydrogens, might collide with another just like it. In an instant they lock together, sharing electrons, forming a new stable molecule, ethane. It's a substance familiar to us on Earth, simple hydrocarbon. On Titan, its creation marks the first step up a vast ladder of complexity, a process of molecular construction that never ever stops. The sun's energy, once destructive, has now become a creative force powering a planetary-scale organic factory. And this factory has been running without interruption for longer than life has existed on Earth. The process doesn't end with ethane. The atmospheric chaos is far too rich, the possibilities far too numerous. Other more complex radicals are also formed in that initial shattering, and they too begin a frantic dance of combination. They link together in chains, forming propane-butane, the same compounds we use as fuel. They form acetylene and ethylene molecules with double or triple carbon bonds, endowing them with even greater chemical reactivity. It's a cascade of creation, a runaway polymerization where simple molecules are irresistibly stitched together into longer and longer chains. From the wreckage of methane, a whole new chemical ecosystem is born, one that grows more intricate with each passing moment. It's as if you took a single simple Lego brick, shattered it, and found that the pieces could spontaneously assemble themselves into vastly more elaborate structures. This is what Titan's atmosphere does ceaselessly. This chemical ballet gives rise to something even more significant, something that defines Titan's very appearance. As these hydrocarbon chains grow longer, they begin to attract others. Nitrogen, which makes up the vast majority of the atmosphere, is also eventually drawn into the fray. Though far more stable than methane, it too can be broken by high-energy particles from Saturn's magnetic field, creating nitrogen-based radicals. When these nitrogen fragments meet the growing carbon chains, they weave themselves into the structure, creating a class of compounds known as nitriles. These new heavier molecules are sticky. They clump together, moving from a gas to something more substantial. They are the seeds of Titan's haze. Microscopic dust motes far smaller than a particle of smoke begin to form in the highest reaches of the sky. This is the birth of the aerosols, the solid organic particles that collectively create the dense, impenetrable orange smog that has hidden Titan's surface from our eyes for centuries. We call this complex, sticky, reddish-brown stuff tholins, a word derived from the Greek for muddy or unclear. It is a name born of our own ignorance, for we have never been able to perfectly replicate this substance in a lab on Earth. Titan's specific recipe of extreme cold, unique atmospheric pressures and a particular blend of radiation is impossible to match. These tholins are a truly alien material born in an alien sky. As these particles grow, gravity begins to take hold. Slowly, imperceptibly, they begin to fall. A gentle, unending snowfall of complex organic dust drifting down from the stratosphere through the troposphere, a journey that can take hundreds, perhaps thousands of years. This is not a snow of frozen water, but a constant drizzle of carbon, a perpetual inheritance from the sky to the ground. When the Huygens probe made its historic descent in 2005, it saw this process firsthand. It flew through this haze, measuring the particles, tasting the chemical composition of the air. It found a world utterly saturated with the products of this solar-powered factory. The orange colour of the sky you would see standing on the surface, it is the colour of this falling dust, the tint of sunlight filtered through a thick veil of complex organic molecules. The sheer volume of this production is difficult to comprehend. Data from the Cassini mission allowed us to calculate the rate of this atmospheric conversion, and the numbers are staggering. Every single day, the ultraviolet light from the sun manufactures something on the order of 400 tons of hydrocarbons and tholins. 400 tons of solid and liquid organic material is created out of the air and begins its slow descent to the surface. It is an amount equivalent to a fleet of heavy cargo trucks dumping their contents into the atmosphere every 24 hours. Think of what that means over geological time. For 4.5 billion years this process has been running. A continuous gentle rain of carbon compounds has been coating every square inch of Titan's surface. The dark dunes that encircle the moon's equator are not made of silicate sand like the deserts of Earth. They are vast continent-sized fields of solid organic particles, hydrocarbon sand, that has rained from the sky for eons. The floors of the lakes and seas are not bare rock, but are likely coated in a thick primordial sludge of this tholin material, a chemical sediment layer that could be hundreds of meters thick. This revelation transforms our understanding of Titan completely. It ceases to be a simple world of methane, rain and rock. It becomes a dynamic system of immense chemical complexity, a world that is actively generating the raw ingredients for what we don't yet know. On the early Earth, it is thought that a similar though much smaller production of organic molecules may have contributed to the primordial soup from which life eventually emerged. Titan presents us with a version of this process on an unbelievable scale, but in an environment so profoundly cold that the chemistry is forced down entirely different pathways. Here, water is frozen as hard as granite, acting as the bedrock of the world. The active chemistry is the chemistry of carbon driven by methane and powered by the distant sun. It is an experiment in organic chemistry that has been running for the entire lifespan of the solar system, and we are just now beginning to read the results. What is truly tantalizing is the fate of these molecules once they complete their long journey to the ground. They don't just sit there, they are buried by further deposition. They are washed by methane rivers into the depths of the seas. They are subjected to the immense pressures of the overlying landscape. On Earth, carbon under pressure gives us graphite and eventually diamonds. But the material falling on Titan is not simple carbon. It is an extraordinarily complex assortment of hydrocarbons and nitriles, a rich organic tapestry, unlike anything in our terrestrial experience. The sheer abundance of these precursor materials, combined with the unique environmental conditions on Titan, opens up a landscape of chemical possibility that borders on science fiction. The high atmospheric pressure at the surface, 1.5 times that of Earth's, is just the beginning. Beneath the surface, those pressures increase dramatically. What exotic forms of matter might be forged in such an environment, where the starting ingredients are not simple elements, but complex chains and rings of carbon, hydrogen, and nitrogen? The chemistry of the sky is only the first act in a much deeper, much stranger story. It provides a constant, inexhaustible supply of raw material, an endless conveyor belt delivering complex carbon from the heavens to a high-pressure cryogenic laboratory below. And it is in those buried depths under the weight of mountains of organic sand and the crushing pressure of a frozen world that the most extraordinary transformations may be taking place. The sky is the factory, but the crust is the crucible. What then becomes of this buried celestial treasure? What happens to this endless rain of organic dust when it's subjected to the crushing forces and frigid darkness of Titan's deep geology, and so the shattered remnants of methane begin their fall? What you are witnessing is not a storm in any human sense. It is a form of geological weather, a slow-motion cascade unfolding over centuries, a silent, perpetual blizzard of pure elemental carbon descending through an alien sky. These tholin particles, this cosmic soot born in the high, sun-drenched frontiers of Titan's atmosphere, are now castaways, orphans of photochemistry, and they have nowhere to go but down. Gravity, the great undiscriminating cosmic anchor, has taken hold of them. Their journey will be one of the longest and strangest falls in the entire solar system. Imagine yourself sinking with one of these microscopic grains. Initially, the descent is almost imperceptible, a gentle drift through the thin, hazy stratosphere. Below you, the world is a featureless orange shroud, a globe of mystery wrapped in nitrogen and hydrocarbons. But as you descend kilometre by agonizing kilometre, the environment around you begins to transform. The diffuse haze coalesces, thickening from a tenuous fog into a substantial, palpable medium. The ambient pressure, the sheer weight of the sky above, starts to build with an inexorable crushing force. This is not merely an atmosphere, it is a gaseous ocean, and we are sinking toward its abyssal plains. On Earth, we think of pressure in terms of atmospheres, or the immense weight of water in our deepest trenches. But Titan plays by a different set of rules. Here the atmosphere is 1.5 times as massive as Earth's at the surface, despite the Moon's feeble gravity. This creates a pressure cooker environment, a planetary vice that relentlessly squeezes everything within its grasp. By the time our carbon particle has fallen just halfway through the troposphere, the pressure has already multiplied, reaching levels that would feel oppressive, even dangerous to a human. The gas is no longer thin and ethereal. It has a texture, a resistance, as if you were moving through invisible syrup. Deeper still, the numbers become truly astronomical. The weight of 100 kilometres of dense cold nitrogen and methane bears down from above a column of gas so immense it functions less like air and more like a fluid press. At these depths, perhaps 30 or 40 kilometres from the surface, the pressure exceeds anything found naturally in Earth's atmosphere, approaching the conditions sailors experience hundreds of feet beneath the ocean's surface. And our journey is not over. The carbon continues its descent, sinking into a realm of permanent twilight, a place where the sun is a forgotten memory. Here the physics of familiar materials begin to warp and buckle. It is in this profound abyss that the second act of our drama begins, for pressure is not the only actor on this stage. The very methane that was destroyed in the upper atmosphere is still present here in the depths, but in a profoundly altered state. This deep tropospheric methane is not just a simple gas. Under the dual influence of intense pressure and cryogenic cold, it has been compressed into a dense, almost liquid-like phase. It's a bizarre state of matter, a thick supercritical fog that permeates the lower atmosphere, dissolving other hydrocarbons and fundamentally changing the chemical rules of the game. The carbon soot, once drifting in a near vacuum, is now suspended in this potent pressurized methane bath. It is no longer falling through air, it is steeping in a chemical soup. This is the crucible. A place of unimaginable pressure and exotic chemistry, where the fundamental building blocks of life are subjected to forces that can compel them to abandon their old forms and forge new extraordinary identities. Here within this planetary-scale laboratory, the most abundant element of this strange world carbon is poised for a metamorphosis. The lonely disorganized clusters of carbon atoms that make up the soot are now being jostled, compressed, and slammed together with a force they have never before experienced. The space between individual atoms shrinks. Their electron shells normally repelling one another are now forced into an uncomfortable energetic intimacy. This is the dawn of polymerization. It's a term that might sound clinical, but what it describes is a form of microscopic spontaneous alchemy. Polymerization is simply the process of simple molecules or monomers linking together to form long, complex chains called polymers. On Earth, it's the process that gives us plastics, nylon and rubber. Life itself is based on it in the elegant chains of DNA and the complex folding of proteins. But on Titan, in this deep, high-pressure methane sea carbon itself becomes the monomer. The immense pressure acts like a cosmic catalyst, a relentless shepherd, forcing stray carbon atoms into a new flock. It overcomes their natural reluctance to bond in certain ways, providing the sheer physical energy needed to rearrange their structure. Think of it like this: the soot particles are like loose piles of sand. Each grain is an individual amorphous clump of carbon atoms disorganized and weakly connected. But as the gravitational press tightens, these grains are compacted. The individual atoms within them are squeezed so intensely that their fundamental bonds begin to break and reform. The chaotic, jumbled structure of soot is inherently unstable under such duhemispheric stress. The universe prefers order, especially when under duress, and carbon has a powerful preference for creating strong, stable crystalline lattices. The methane-rich environment helps this process along, acting as a solvent that can strip away impurities like hydrogen atoms and allowing purer carbon structures to form. First, the carbon might organize into flat hexagonal sheets, the structure of graphite, the soft material in our pencils. These sheets, just one atom thick, are incredibly strong on their own. We are witnessing the creation of graphene, in essence, forged not in a high-tech human laboratory, but in the heart of a frigid alien atmosphere. These microscopic sheets, trillions of them, begin to stack and align, pushed together by the unyielding pressure. But the journey does not end with simple graphite. The pressure continues to mount as the particles sink ever lower, and the flat, two-dimensional sheets of graphite are themselves put under a strain they cannot withstand. The universe is demanding an even more compact, more stable, more energy-efficient configuration for these carbon atoms. It is here that we stand at the precipice of a truly radical idea, a concept born from the intersection of planetary science, high-pressure physics, and pure chemical intuition. What happens to carbon when it's subjected to hundreds, perhaps thousands of times the atmospheric pressure of Earth, all while being bathed in a sea of liquid-like methane at temperatures of 200 degrees below freezing? To find the answer, scientists turned not to telescopes, but to laboratories on Earth using devices of extraordinary power. They used diamond anvil cells, instruments capable of recreating the titanic pressures found deep within planets. By squeezing tiny samples of hydrocarbons like acetylene and benzene, which are known to exist on Titan, they tried to simulate the conditions in the Moon's deep atmospheric crucible. The results were astonishing. Under pressures analogous to those deep within Titan, these simple hydrocarbon molecules, the very kind produced by the breakdown of methane, spontaneously transformed. They polymerized their carbon atoms, rearranging themselves into far more complex and durable structures. But as the pressure was cranked even higher, something else happened. The carbon atoms, once content in their flat graphitic sheets, were forced into a new three-dimensional arrangement. The bonds between them buckled and reformed, snapping into the strongest and most compact configuration that carbon can adopt, the tetrahedral lattice. This is the structure of diamond. Now we must be precise. The diamonds forming in these experiments and theoretically on Titan are not the flawless, brilliant-cut gemstones of jewellery. Such perfection requires immense time and stable high temperatures, like those found deep within the Earth's mantle. Titan's environment is far colder and chemically messier. Instead, the science points toward the formation of what are called diamond-like polymorphs, or even more intriguingly, co-crystals of hydrocarbon and nitrogen. These would be incredibly dense, hard crystalline structures, microscopic in scale, possessing the fundamental tetrahedral bond of a true diamond, but perhaps clouded with impurities or interlinked with long polymer chains. Imagine a substance with the hardness of diamond but the complexity of plastic, a new state of carbon matter forged in an environment unlike any on Earth. These are the methane diamonds. The theory therefore paints a breathtaking picture. For billions of years since the dawn of the solar system, the sun's ultraviolet light has been relentlessly breaking apart methane molecules in Titan's upper atmosphere. For billions of years, the resulting carbon dust has been drifting down into the high-pressure depths, and for billions of years that deep atmospheric furnace has been compressing this raw carbon, polymerizing it, and crystallizing it into its densest possible form. This isn't a fleeting momentary weather event. It is a continuous planetary-scale industrial process, a diamond factory running uninterrupted for eons. The sheer quantity of carbon involved is difficult to comprehend. Titan's atmosphere is rich with it, and the process of methane destruction and carbon rain is incredibly efficient. Over geological time, what would be the result? The tiny newly formed diamond-like crystals, being significantly denser than the surrounding nitrogen-methane atmosphere, would continue their inexorable fall. They would precipitate out of the sky a slow glittering rain of superhard carbon settling onto the surface below. We are forced to confront a staggering possibility that the vast shifting dune fields of Titan, those dark equatorial bands that stretch for thousands of kilometers, might not be made of simple hydrocarbon sand or water ice. What if mixed in with the organic sludge or even composing the bulk of the dunes are trillions upon trillions of tons of these diamond-like crystals worn down over ages into a fine, dark, incredibly hard sand? Could the riverbeds carved by flowing liquid methane be glittering not with silica pebbles but with carbon jewels? When the Huygens probe landed on Titan in 2005, it saw a floodplain littered with rounded stones, which scientists assumed were made of humble water ice, frozen as hard as rock at those temperatures. But the theory of methane diamonds offers another more radical interpretation. Could those rocks have been agglomerations of this precipitated carbon cemented together over millennia? The implications are profound, suggesting a surface geology and entire world shaped and sculpted not by silicon-based rock, but by a foundation of exotic high-pressure carbon. This process would fundamentally alter our understanding of the Moon's entire carbon cycle. It would represent a one-way journey for carbon, a permanent sink. Methane is destroyed in the sky, its carbon turns into diamond, and that diamond, being one of the most stable and inert substances in the universe, is then locked away on the surface, sequestered from the atmospheric cycle forever. This raises a deep and troubling paradox. Given the rate at which the Sun destroys methane, Titan's entire atmospheric supply should have been depleted billions of years ago, all of it converted into soot, and theoretically into these diamond deposits. And yet the methane is still there, thick and abundant. Something must be replenishing it, resupplying the atmosphere from a vast hidden reservoir. The diamond rain is not just a curiosity. It is a clue, a breadcrumb trail leading us toward an even deeper mystery hidden beneath Titan's frozen crust. The science is sound, the laboratory experiments are compelling, and the logic is inescapable. The ingredients are all there, an endless supply of carbon pressures that rival those deep within planets, and billions of years for the chemistry to unfold. The formation of these exotic carbon polymorphs is not just possible. In such an environment, it may well be inevitable. We have followed the journey of a single carbon atom from the top of the sky to the crushing depths, witnessing its transformation from a simple gas into the most resilient material known to science. We have laid the theoretical groundwork piece by painstaking piece for a moon where it truly rains diamonds. But theory, no matter how elegant, is not proof. Laboratory simulations, no matter how precise, are not reality. We have built a compelling scientific case, a ghost story told with physics and chemistry. Now, we must go hunting for the ghost. How do you find evidence of something so extraordinary on a world nearly 1 billion miles away? A world permanently veiled by an impenetrable orange haze? How do you search for diamond dunes or crystalline riverbeds, using only the remote eyes of a robotic spacecraft? The challenge seems insurmountable, Yet it is a challenge that we in our relentless curiosity were destined to accept. The search for Titan's diamonds would require us to push our technology and our ingenuity to its absolute limit, and so we have arrived at the precipice of an almost unbelievable conclusion. All the evidence we've gathered, from the churning orange haze to the whisper of cryovolcanic engines deep beneath the ice, has led us to this single staggering question: could a world really rain jewels? The components, as we have seen, are all present. You have the raw material in almost inexhaustible supply carbon locked away inside the methane molecule, the very lifeblood of Titan's atmosphere and its frigid seas. You have the titanic pressures, a force so immense that it beggars belief, an atmospheric weight that multiplies with every kilometre of descent into the moon's mysterious depths. And you have the required energy, the violent spark needed to shatter the strong chemical bonds of methane and liberate the carbon atoms within. The puzzle pieces are scattered across the board. Now here in the heart of our journey we must assemble them. We must construct the full, breathtaking hypothesis, the scientific story of how a moon could forge diamonds in its sky. Our story begins high in the stratosphere, some 300 miles up, where Titan's atmosphere is still a thin ethereal shroud. Down here, methane exists as a vapour, a trace component, but its destiny is written not in the placid upper layers, but in the violent turmoil that awaits far, far below. Imagine you're a single particle of carbon bound to 4 hydrogen atoms, a methane molecule adrift in this alien sky. You begin to fall, not quickly, but as a slow, inexorable drift pulled down by gravity's faint but persistent tug. For weeks, months, perhaps even years you descend. The pressure around you mounts subtly at first, then with crushing insistence. The thin haze thickens into an opaque soupy fog. This is the cosmic anvil, the great press of Titan's atmosphere, and it is only now beginning its work. As we sink deeper past the 100-mile mark, the conditions transform into something truly hellish. Here in the dense troposphere, the pressure is already far greater than at sea level on Earth, and the temperature, while still cryogenic, begins to rise from its stratospheric lows. It is within this cauldron that the first act of creation must occur. Scientists propose 2 primary mechanisms for the initial violent trigger, 2 competing theories for the celestial forge that starts it all. The first is a spectacle of raw, untamed power lightning, not the fleeting flashes we know on Earth, but monstrous superbolts arcing through the nitrogen and methane clouds. These are not storms of water, but of liquid natural gas, and the electrical discharges they could generate would be cataclysmic. Each flash a celestial blowtorch 100 times more powerful than any on Earth would tear through the surrounding atmosphere. In the millionth of a second that the bolt exists, the temperature inside its channel would spike to tens of thousands of degrees hotter than the surface of our own sun. For the methane molecules caught in this inferno, there is no escape. The intense heat and electrical energy would be more than enough to shatter their molecular bonds, a process known as pyrolysis. The 4 hydrogen atoms are ripped away, leaving behind a lone liberated atom of pure carbon. In the wake of the lightning, a plume of elemental carbon dust, a fine black soot, would begin to bloom and expand in the thick orange air. The second hypothesis is perhaps even more alien, originating not in the sky, but from the very heart of the moon itself. We have seen the evidence for cryovolcanism, for great plumes of material erupting from Titan's interior. These are not volcanoes of molten rock, but of a super-pressurized slurry of liquid water, ammonia, and dissolved methane blasting upwards through the icy crust with tremendous force. As this plume punches through the surface and screams into the dense lower atmosphere, it creates a transient localized zone of extreme chemical chaos. The rapid, violent decompression and the immense temperature differential between the warmer interior slurry and the frigid air could create a perfect temporary crucible. Here, too, methane molecules could be torn asunder, not by lightning, but by the sheer shock and thermal violence of the eruption. The cryovolcanic plume becomes a fleeting chemical factory, seeding the atmosphere with a vast cloud of newly freed carbon atoms. Whether by lightning's flash or volcanic fury, the result is the same: a fine dark dust of pure carbon now hangs suspended in Titan's sky, a ghostly powder of potential, and its journey has only just begun. Now the real alchemy starts driven by the relentless invisible hand of pressure. This carbon soot, this primordial dust, continues its slow descent. It drifts downwards through the troposphere, sinking deeper and deeper into the Moon's gravitational embrace. At 200 kilometers down, the pressure is intense. At 100 kilometers, it is suffocating. But the true transformation begins much deeper in a region of the atmosphere we have never directly witnessed, a place where the weight of the sky above is almost beyond our comprehension. Imagine a depth of over 1,000 kilometers into the gaseous envelope where the pressure has ramped up to thousands, even tens of thousands of times that of Earth's surface. Here the very nature of matter begins to warp. The individual atoms of carbon in the soot are being squeezed together with a force equivalent to the weight of a mountain. They have no choice. They must reconfigure. The loose amorphous structure of soot is energetically unfavourable under such duress. The universe prefers order, efficiency and stability, and under this titanic pressure the most stable arrangement for carbon atoms is a tightly packed, perfectly interlocking crystal lattice. The atoms begin to link up, forming the powerful tetrahedral bonds that are the unmistakable signature of a diamond. This is not a process of instantaneous creation. It is a gradual metamorphosis occurring as the particles fall. They are not gemstone-quality crystals, not the flawless jewels of our earthly crowns. These would be something far stranger. We must picture them as microscopic, perhaps only nanometers, or micrometers in size, imperfect, likely cloudy or even black from impurities. Think less of a singular perfect gem, and more of a crystalline hail. A blizzard of diamond dust, a fine hard grit precipitating from the sky. Scientists on Earth have simulated this incredible process. In laboratories, they use devices called diamond anvil cells to squeeze tiny samples of methane between the tips of two brilliant cut diamonds, recreating the colossal pressures of a gas giant or a moon like Titan. They then blast the sample with a powerful laser simulating the energy of a lightning strike, and under our own eyes in these tiny controlled experiments the methane breaks down. The carbon precipitates out, and through spectroscopic analysis we can see it forming the unmistakable crystal structure of nanodiamonds. The theory is not fantasy. It is born of repeatable observable physics. The conditions exist on Titan. The ingredients are present. The laboratory results confirm the process is possible. The conclusion, however improbable it sounds, becomes deeply compelling. For millennia, this diamond dust would fall. A slow, perpetual, invisible shower of hard carbon, drifting down through the deepest, murkiest layers of the atmosphere. But what happens when it finally reaches the end of its journey? Where does this celestial treasure accumulate? The answer could be one of the most spectacular sights in the entire solar system. Much of Titan's surface, as we've explored, is covered in vast dark dunes. We have long assumed them to be composed of tholins, the complex organic solids that give Titan its orange colour. But what if they are not just tholins? What if over billions of years this falling diamond dust has mixed with the organic sands, seasoning the dunes with a fine, glittering abrasive of extraordinary hardness? The endless fields of Titan's equatorial deserts might not just be organic, but crystalline great ergs of carbon sand and microscopic diamond grit sculpted by the gentle methane winds. A landscape that glitters under the faint distant light of Saturn. There is another even more profound possibility. We know Titan has seas, vast placid bodies of liquid, not of water, but of methane and ethane. Ligeia Mare Kraken, Mare Punga Mare. These are not just lakes, they are alien oceans. A diamond, being a dense form of carbon, is significantly heavier than the liquid methane and ethane of these seas. So any diamond dust that falls over these great bodies of liquid would not float or dissolve. It would sink. Slowly, gracefully it would descend through the liquid hydrocarbon depths, past the point where the dim sunlight can penetrate into the absolute crushing blackness of the abyssal plain. Over geologic time, over hundreds of millions of years, this process would create something utterly astonishing on the seabed. Not mud, not silt, not sand, but a layer of pure crystalline carbon. A sedimentary bed of diamonds. Imagine a future submersible, a probe designed to withstand the cold and the pressure descending into the depths of Kraken Mare. Its lights switch on, cutting through the perpetual gloom. And what they reveal is not a familiar seabed, but a dark, smooth, strangely reflective plain, a consolidated layer of diamond material stretching for miles in every direction, the accumulated wealth of a sky that has rained jewels for eons. This layer might not be loose dust. Under the pressure of the deep sea and the weight of subsequent layers, it could become a solid diamond-like crust at the bottom of the methane ocean, a unique form of geology found nowhere else we know of. This process would fundamentally rewrite the carbon cycle of Titan. On Earth, carbon is cycled through life, the atmosphere, the oceans, and the rocks. On Titan, it appears to be a one-way street, a downward cascade. Methane is destroyed in the upper atmosphere to create tholins and potentially diamonds. These heavier materials then fall to the surface, permanently removing carbon from the atmospheric inventory. This leads to a deep paradox. Titan should have run out of methane long ago. The fact that its atmosphere is still rich with the stuff is the strongest indirect evidence we have that it is being actively replenished from below, most likely by the very cryovolcanic activity that may also help forge the diamonds. It is a complete interconnected system, a dynamic engine where geology and meteorology are locked in a spectacular creative dance. The falling diamonds are not just a curiosity, they are a vital clue to the inner workings of this world, a signpost pointing to the geological activity churning within its heart. What we are describing is a world built on a foundation of carbon in its most extreme and exotic forms. An atmosphere that creates organic smog lakes of flammable liquid sands of complex polymers, and in its deepest heart a rain of gems. It is a vision that pushes the boundaries of what we thought a moon could be, transforming it from a simple frozen satellite into a dynamic and complex planetary laboratory. The idea challenges us to expand our imagination to accept that the laws of physics, when applied to alien ingredients and alien conditions, can produce outcomes that seem torn from the pages of mythology. We are no longer just looking at a moon. We are bearing witness to a world where the most precious material on Earth is a form of weather, a meteorological byproduct of a vast alien cycle. The central question of our journey has found its answer not in a simple yes or no, but in a detailed, plausible, and scientifically grounded model that is as elegant as it is shocking. But this grand synthesis, this climax of our investigation, inevitably gives birth to a new and even more profound set of questions. If a world can rain the very building blocks of diamonds, if its surface is a repository for an endless supply of complex organic chemistry, and if there is liquid, albeit liquid methane in which this chemistry can unfold, what other miracles might be possible? The rain of diamonds is a testament to Titan's exotic geochemistry. But might this same extraordinary environment with its unique confluence of carbon energy and liquid also hold the key to a different kind of creation? A creation not of crystals, but of complexity. Of life itself. The stage is set, the ingredients are present, and as the last of the diamond dust settles in the abyssal depths, we must now turn our gaze from the sky to the seas and ask the ultimate question. And so, our journey across this frozen echo of a primeval Earth reaches its end. We have travelled from the hazy, impenetrable shroud that once concealed a world to the very shores of its liquid methane seas. We've soared over dunes of solid hydrocarbons and stood at the foot of mountains made of water ice, harder than granite in the crushing cold. What began as a single enigmatic point of light in Cassini's cameras has resolved into a landscape of staggering complexity and profound weirdness, a world that has systematically dismantled our expectations for what a moon can be. It is a testament to the universe's boundless imagination, a place that forces us to reconsider the very definitions of weather geology, and perhaps even life itself. We came seeking a simple world, a planetary antique preserved in deep freeze. What we found instead was a dynamic breathing system, a moon with a beating heart powered not by water but by methane. We have seen how this simple molecule, a gas on our own world, assumes the central role that water plays on Earth. It evaporates from vast placid lakes, forming clouds that drift through a nitrogen sky. It then condenses and falls as rain, a slow viscous drizzle that carves river channels into the icy bedrock. This methanological cycle, a dark mirror to our own hydrological one, is the engine that drives all of Titan's surface geology. It is a process both alien and deeply familiar, a planetary rhythm that resonates with our own experience, yet is composed of substances that would be utterly lethal to us. This duality lies at the core of Titan's profound allure. It is a world that whispers of home, in a language we are only just beginning to decipher, a place where the fundamental physics of planetary science are expressed in a vocabulary of exotic cryochemistry. Our models, once so certain, have been broken and rebuilt, here expanded to include possibilities we had never before dared to entertain. We learned that beneath the veneer of familiar forms, the lakes, the rivers, the dunes, lies a geology of pure strangeness. The very ground beneath your feet is not rock but water ice, frozen to such an extreme temperature that it behaves like silicate rock on Earth. The mountains are not upwellings of magma, but tectonic blocks of this ice pushed and folded by immense slow-moving forces. The volcanoes, if they exist, do not spew molten lava but a cold, viscous slurry of water and ammonia, a cryomagma that freezes into new land. Every feature on this world is a paradox, a geological riddle wrapped in a cryogenic enigma. We have had to invent a new language to describe it, a lexicon of cryovolcanism and hydrocarbon tectonics, because the rulebook of Earth-based geology simply does not apply. Here water is the bedrock, and liquid hydrocarbons are the erosive force that shapes it. This intricate dance of alien chemistry and physics led us step by painstaking step to the most startling and magnificent revelation of all. A conclusion born from the inescapable logic of pressure and temperature, a hypothesis that sounds like pure mythology, yet is grounded in the uncompromising laws of chemistry. We followed the methane from the sky to the seas, and then we plunged deeper into the crushing abyss of Titan's interior. We calculated the immense pressures that must exist miles below the surface, pressures that build within the moon's icy mantle, squeezing the very atoms of the liquid hydrocarbons that seep down from above. Here, in this natural high-pressure laboratory, we confronted a transformation that borders on alchemy. The simple 4-hydrogen, 1-carbon structure of methane begins to break. Under pressures hundreds of thousands of times greater than Earth's atmosphere, the bonds holding the methane molecules together are ripped apart. The hydrogen atoms are stripped away, and the carbon atoms, now liberated, find themselves in an environment of unimaginable compression. They are forced closer and closer together, seeking a new, more stable configuration. They begin to link up, forming the strongest bond in all of chemistry, the tetrahedral lattice of a diamond. This is the heart of the theory, the stunning climax of Titan's chemical story. Deep within this frigid moon, the universe is performing an act of cosmic jewelry making. It is forging diamonds not from pure carbon under volcanic heat, but from simple methane under cryogenic pressure. These are not the diamonds of Earth born in fire and fury. These are ice diamonds, alien gems formed in the cold, dark depths of a hydrocarbon world. And the process doesn't end there. As these newly formed diamondoids or even larger diamond structures accumulate, they become heavier than their surroundings. They would begin to sink, a slow, steady rain of crystals falling through the moon's deep interior, a perpetual silent hailstorm of jewels in the dark. Over geological time, this process could create vast layers of diamond deep within Titan, a core of unimaginable wealth and scientific wonder, forever locked away beneath a crust of ice. This is not mere fantasy. The calculations are robust. The chemistry is sound. While we have yet to directly observe it, the evidence points toward a reality where a moon in our own solar system is a factory for the most precious of terrestrial gems, using the most common of organic materials as its feedstock. It redefines our entire concept of planetary resources and processes, suggesting that the universe's chemical pathways are far more exotic and creative than we ever imagined. The idea of a methane diamond rain fundamentally alters our perception of Titan, transforming it from a curious oddity into a world of unparalleled chemical extremity. Yet the implications of this extreme chemistry extend far beyond geology. They reach into the deepest, most fundamental questions we can ask about the cosmos, the question of life. Titan is and has been for billions of years a planet-scale experiment in prebiotic chemistry. Its atmosphere is a thick organic soup constantly irradiated by sunlight. This ultraviolet radiation acts as a celestial spark plug, breaking down the nitrogen and methane and allowing them to recombine into an incredible diversity of complex organic molecules. These molecules, known as tholins, are the building blocks of proteins and nucleic acids, the very components of life on Earth. They are the reddish-brown soot that coats Titan's surface, the material that makes up its vast fields of dunes. For eons, this moon has been manufacturing the raw ingredients for biology on an industrial scale. It is an environment that tantalizingly resembles some theories of Earth's own primordial past before life began. But Titan adds a crucial confounding twist: the extreme cold and the absence of liquid water. Life as we know it is inextricably tied to water. It is the universal solvent, the medium in which the chemical reactions of biology take place. On Titan, that role is played by liquid methane and ethane. Could life in a form so alien we can barely conceive of it arise in such a solvent? Could biology exist without water? This is one of the most profound questions in modern science, and Titan is our only laboratory to study it. Perhaps life there would use a different kind of cell membrane, one soluble in liquid methane. Perhaps its DNA equivalent would be built from a different backbone, one stable at cryogenic temperatures. It would be life, but not as we know it. And this is where the methane diamonds re-enter the story in a way that is truly mind-bending. The process that could form diamonds, the breakdown of hydrocarbons under pressure, is also a process that organizes carbon into complex stable structures. Could this be a pathway for concentrating and structuring the raw organic material raining down from the atmosphere? Could the formation of diamondoids and other complex carbon lattices provide a template, a scaffold upon which even more complex prebiotic molecules could assemble? It's a speculative leap, but on Titan, such leaps are necessary. We are witnessing a world where carbon, the fundamental element of life, is subjected to a range of conditions that exist nowhere else in our solar system. From the gentle radiation in the upper atmosphere to the unimaginable pressures deep in its core, Titan is exploring the full potential of carbon chemistry. It is testing the limits of organic complexity. It is possible that the journey towards life does not require a warm, watery pond, but could begin in a cold, dark, high-pressure crucible, where methane itself is transformed into the seed of something extraordinary. The moon where it rains diamonds might also be the moon where the seeds of an entirely new biology are being forged. These are the immense, tantalizing questions that Titan has laid before us. They are questions that cannot be answered from orbit. They cannot be solved by a fleeting flyby. To unravel these mysteries, we must go back. We must land. We must touch the surface, breathe the atmosphere, and sample the materials of this alien world directly. And that is precisely what we're going to do. The next great chapter in our exploration of Titan is already being written. It is a mission of unprecedented ambition, a machine of incredible ingenuity designed to take us closer to the truth than ever before. It is called Dragonfly. This mission is not a lander in the traditional sense, a static laboratory fixed to one spot. No, for a world as diverse and complex as Titan, we need a different approach. Dragonfly is a nuclear-powered dual quadcopter drone, a robotic explorer capable of flying through Titan's thick, hazy atmosphere. Imagine a machine the size of a small car with 8 rotors, designed to make multiple flights across the surface of another world. Taking advantage of Titan's high atmospheric density and low gravity, Dragonfly will be able to fly for miles at a time, leapfrogging from one scientifically compelling location to another. Its journey will be a multi-year odyssey, an aerial tour of one of the most exotic landscapes in the solar system. The chosen landing site is the Shangri-La Dune Field, a vast sea of the dark organic tholin sands we have spoken so much about. This is ground zero for understanding the raw materials available for life. Upon landing, Dragonfly will deploy its instruments, a sophisticated suite of tools designed to read the chemical history written in Titan's soil. Its mass spectrometer, called DRUMS, will be its primary tool for discovery. It will drill into the surface, collecting samples of the icy ground and the organic sediments, and then heat them in a tiny oven. As the samples vaporize, the instrument will analyze their composition with exquisite precision, searching for the key prebiotic molecules, amino acids, nucleotides, the very building blocks of life. It will be searching for biosignatures, chemical fingerprints that could hint at biological processes past or present. Has life ever taken hold in this methane world? DRUMS will give us our first real chance to find out. But Dragonfly is more than just a chemistry lab. It is a fully equipped geological and meteorological explorer. Its gamma-ray and neutron spectrometer, DRE-GNS, will probe the composition of the ground beneath it without even touching it, determining the ratio of water ice to organic solids. Its meteorology sensors, DRE-GMET, will measure the temperature, pressure and wind, giving us our first on-the-ground weather report from Titan's surface, perhaps even capturing the signs of a distant methane storm. Its cameras will provide us with a human-scale view of this incredible world. We will see the grains of organic sand, the texture of the frozen ground. We will see the landscape from the perspective of an explorer, standing on the surface looking out at an alien horizon under a hazy orange sky. And then after days of study in one location, the command will be sent from Earth. The rotors will spin up and Dragonfly will lift off, ascending back into the skies of Titan to fly towards its next destination. Its ultimate target is the Selk crater, an impact structure believed to be relatively young. Here the impact is thought to have melted the water ice crust, creating a temporary pool of liquid water that mixed with the surface organics. For a few thousand years, this crater may have been the most habitable place on Titan, a transient oasis where liquid water, organic molecules and energy were all present in one place. What happened there? What chemical reactions took place? Did this fleeting moment of warmth and water kickstart a more complex biological journey? Dragonfly will fly there to find out. It will land within the crater, sample the materials and read the story of this ancient melted impact zone. This mission is our direct response to the call of Titan. It is the physical embodiment of our curiosity, a robotic emissary sent to touch, taste and analyze this world on our behalf. It will search for the answers to the questions Cassini could only ask. It will tell us if Titan's chemistry is truly on a path toward life. And it will provide the crucial ground truth for our most audacious theories, including the potential for high-pressure minerals formed from hydrocarbons. While Dragonfly itself cannot drill deep enough to find methane diamonds, its detailed analysis of the surface composition and geology will provide critical context. It can search for evidence of cryovolcanic flows that might have dredged up materials from the deep interior, providing clues about the processes happening far below. It will refine our models of Titan's structure, giving us a clearer picture of the temperatures and pressures within, and strengthening the case for or against diamond formation. Dragonfly is the next logical step, a bold leap into the unknown that will transform Titan from a world of tantalizing possibilities into a world of concrete data. So we stand at a precipice of discovery. Behind us lies the incredible journey of Cassini, a mission that painted the first detailed portrait of a world more wondrous than we could have dreamed. Ahead lies Dragonfly, a mission that promises to add texture, colour, and astonishing new detail to that portrait. Titan has challenged us. It has expanded our science, broadened our horizons, and forced us to think more creatively about the nature of worlds. It has shown us that the universe is not limited by our terrestrial experience. The cosmos is a far more diverse and surprising place, capable of creating planetary systems of breathtaking variety. It can create a world of rock, a world of gas, and as we have seen, a world where ice behaves like rock and hydrocarbons flow like water. Titan is a crucial piece of the cosmic puzzle. It is an unparalleled natural laboratory, a control experiment for planet Earth. By studying its unique brand of chemistry, we learn more about the fundamental rules that govern the formation of all planets, including our own. It helps us understand the conditions that may have existed on the early Earth, and it provides a stark, beautiful example of an alternative evolutionary path a planet can take. It reminds us that the question, "Are we alone?" is not just about finding another Earth. It's about being open to the possibility of life in forms and environments so profoundly alien that they defy our current definitions. The search for life may not be a search for our reflection in the cosmic mirror, but a search for something entirely new. From a mysterious orange orb to a complex living world of methane rain and organic sands. From a scientific curiosity to a prime target in the search for extraterrestrial life. This has been the story of Titan. It is a story of exploration of human ingenuity and of the relentless desire to understand our place in the universe. We look out into the darkness between the stars and we find not emptiness, but possibility. We find worlds that challenge our assumptions, ignite our imaginations, and inspire us to continue the journey. Titan is no longer just a moon of Saturn. It is a destination. It is a promise. It is a reminder that the most incredible wonders may be hidden in plain sight, veiled by a hazy sky waiting for us to come and look and to ask the right questions. The answers are out there written in the chemistry of a world where it might just rain diamonds, and we are on our way to read them.